Hello, this video is named Determining the Required Sample Size. It is still part of the confidence interval material. And what we're trying to do here is suppose if we were creating a confidence interval and we wanted some specific conditions associated with it. In other words, we wanted to determine what confidence level that we want. And let's say we also want to determine the margin of error in advance. Can we keep it within a certain amount of units? To do that, we want to know what would be the sample size necessary to accomplish that goal. So yes, you can do that, but you have to solve for what would the appropriate sample size be to find this. So let's take a look. We're going to use these. Some books use them with Z and do them with T also. We're just going to treat these as Z's only. So you would be given the population standard deviation. And notice I'm only using one formula here. The margin of error formula for the Z and not the T. And what's happening here is if they took the margin of error formula and then just algebraically solved it for n. So this formula in the red is the one that you're going to be working with. It's going to be your critical confidence level value that we've seen before times the standard deviation divided by the margin of error. And I mentioned up here that, sometimes a problem might directly tell you a margin of error, but sometimes it may say, we want to get a confidence interval to within 3 units or within 1.7 or whatever. So within is a common word to also indicate margin of error. But if it just straight out says margin of error, then nothing to worry about. Now this is very important here that you must always round up to the next integer. Because technically you haven't reached your goal at the lower sample size, so you have to go up to the next one to actually reach it. So very important, whether it's you're doing like my math lab homework or perhaps if on an exam you had 2 consecutive answers, like for this one, if you did the calculation, you got 49.3 and you saw answer choices of both 49 and 50, you pick 50. It's not your normal 0.5 rounding. Any value with a decimal would go up to the next integer above it. So let's just try some examples. That's it. There's not a pre-programmed formula on the calculator like there is for T interval and Z interval, but this is not complicated to plug this in there. Just don't forget to square it. Sometimes I see people forget to type in the square. So I'm not holding out on you. No, there's not a calculator program that's in there in the TI. So, all right. So we're going to say determine the minimum required sample size if you want to be 90% confident that the sample mean is within 0.5 units of the population mean, given that the population standard deviation is 3.4. Assume the population is normally distributed. All right. So this one is going to be one of our standard ones off of the chart here, 90%. I'll go to the larger version of it here, but there's a little snippet of it. Not this one, but this one. And remember the Z's are across the top row, so we're not using the degree of freedom thing here. So 90%, it would be 1.645. All right. So 1.645 is my critical value. The margin of error is given as 0.5. The standard deviation is given as 3.4. So all we have to do is plug it right into this formula. It's not very difficult at all. So you take 1.645 times 3.4, divide by 0.5, and notice I have a square wrapped around all that. So you have to square it. I don't think there's any point in me typing this in the calculator because it's like I said, there's not like a step or for a program you have to follow, calculation. It's just straight up numbers there. So I'll be doing one for a problem that's not solved here shortly, so you'll see me do it then. But notice the answer came out to be 125.1 blah, blah, blah. But notice what I put for the answer. 126, the next highest integer. And that's essentially it. Let's just keep trying some examples. Now here's one coming up. This will give us a refresher of how to come up with the critical value for a confidence level that's not on that chart. But part A is, okay, cheese. So the estimate must be 0.4 milligrams cholesterol content of the cheese. We want to know what sample size to construct a 95% confidence interval that will give us that margin of error with this population standard deviation of 2.8. All right, so we know two of the three numbers there. So 2.8, we know 0.4. Now we need the number that represents 95%. Right here on the top row, 1.96. So all we have to do, right over here, we go 1.96 times that standard deviation of 2.4 divided by 0.4, then we square all of that. And 188.23, blah, blah, blah. I just kind of use the squiggly. It doesn't matter whether I have the squiggly approximately or the equal. It doesn't make any difference. We still want to say the answer is 189. And that's basically it. Now, part B is interesting because it says a 74% confidence interval. So this will kind of go back to something we've seen before on the Z interval process. So what you do is you take, you can do the inverse norm, obviously, if you're using the calculator. If not, I'll show you on the chart how to find it real quick. But you take 1 plus the confidence level as a decimal, all divided by 2. So notice how I've got parentheses here, very important. So it's 1 plus 0.74. So basically it's 1.74. Divided by 2 is 0.787. So if we're doing the chart, we go inside the chart, and I want to find the closest area, not this chart, to 0.87. So let me look for that. And 0.87 is, I was thinking a different number. Between these two, 0.87 is between those two, but it's closer to, you want to pick the closest one, 8708. And then so that's in the 1.1 row and the 0.03 column. So the Z that corresponds to a 74 percentile value, or confidence level, which we then converted to a percentile by going 1 plus confidence level over 2. That's what you're doing by doing that. You're making it to a percentile. So we converted to the 87th percentile. So that's 1.13. And there it is, 1.13. So at that point, we just put in 1.13 times 2.8 divided by 0.4. We're still using the same numbers as part A. Squared, 62.56, yep, goes, so we call that 63 as our answer. This one's a little sneaky. I just kind of threw this in there. I don't know if you honestly would run across that in the online homework or on an exam, but still, just in case. 90% confidence interval within 2 pounds, so the margin of error is 2. But here's kind of the tricky part. It says the variance is 49 pounds. This goes way back to something we learned earlier in the course, that standard deviation is always the square root of the variance. So if the variance sigma squared is 49, the standard deviation would be the square root of 49, which would then be 7. So that's the trickiest part of this problem for sure. 90%, that's right off that chart, not this one. 1.645, so that's easy enough. So that was a little tricky, knowing to take that square root, but just watch for words like that, variance, not standard deviation. So it's 1.645 times 7 divided by 2, 33.15. We round that up to 34. Now let's take a look at this one. Alrighty. Standard deviation is 0.25, 95% confident. within 0.02. So that's your margin of error, 0.02. And 95% is right here, 1.96. Right there. So you take 1.96, that z-value, times 0.25, the standard deviation, divided by the margin of error, which is 0.02. You square all that, and then round it up. You 600.25, you round up to 601. I did this a little differently. That I showed it before the square, which you don't need to do, but I just wanted to point that out. I'm not saying every time you have a multiple choice problem, this is always going to happen, but it can happen. So notice that if you forgot to square this first one, it says 24.5, and if you didn't square it, you would have picked A as the answer. I mean, I've seen that happen, but that's pretty rare. So even, don't forget the square right here, as I mentioned right there. So that's the only reason I did it this way. Normally, I just wouldn't even have done that top line like that, only because I knew that answer was there. So, all right. So that's just more of, FYI. Please be careful. Now, this problem is a little bit tricky, only in the sense that they've got the mean in the problem that we don't need it. The mean, if we were actually calculating a confidence interval, then yeah, we would need the mean. So they kind of threw that in there as an extra number. We don't need that. We have the standard deviation, which is 0.1. And you see it says within 0.025. And then 99% confidence. So you have to kind of ignore that 13.5 because it's not one of the three numbers that we need. 99% confident, here we go. Right there, 2.576. So it's 2.576 times 0.1 divided by 0.025. Square all that, and it's 106 point something, whatever, point whatever. That automatically makes it become 107. Excellent. Okay, here, so there's what I just said, typed out there, that we don't need the 13.5. So let's take a look at this one. I could try to write this. I'm not using a tablet PC, so I would have to kind of make it look sort of ugly here, but I'm going to put it in the calculator anyway, so that's probably good enough, really. I don't think I have to write it out. All right, incomes of college graduates in China. Population standard deviation is 1,200. There's one number. The 95% confidence interval, that's going to lead to our second number. And then within 6250, that's our margin of error. So 95% is 1.96. So if I try to sort of rough hand this out here, it's going to be 1.96. I'm using a mouse pad to do this. And you can see it's not going very well. Times 1,200. Ooh, I'm definitely not going to leave this in the notes. Divided by 6250. Oh, it looks like a square root. 62.5 squared. All right, now let's put this in the calculator. We're going to clear that. We're going to say 1.96 times 1,200. Divided by 62.5 squared. Enter. Round up to the next whole number, 1417. And there it is. Answer C, 1417. Well, okay, that concludes this video on finding the required sample size.